Okay, so I, as an organizer, so I don't know how to say it's a little embarrassing, but I should thank Tuyen for initializing this workshop. So this work is journal with him. So in this talk, first I will give you a motivation to this dynamical approach. And then I will talk about this dynamic degree comparison problem. And then I will introduce you what the dynamical correspondence are. The second part is our results. The first one is on this dynamical degree comparison. The second result is a quantitative version of the standard conjecture C. So we propose this version, which is weaker than the whole standard conjectures. So which might be used to prove with conjectures. And then if I still have time, then I will also talk about a little bit on these relations with the usual standard conjectures. So first of all, let me recall what is the Riemann hypothesis. So say X0 is a smooth project variety of a finite field FQ. Then let X be the best change of X0 to algebraic closure FQ bar. And let F be Frobenius endomorphism of this X with respect to FQ. Then by this Grothendieck Lefschetz track formula, so we know the number of FQ endpoint of this variety can be written in terms of alternating sum of traces of the Fm, the nth iterate of Frobenius action on eta common group. So this could be used to show that the data function of this variety is equal to this product. So the product of the determinant of this Frobenius action, with alternating sign here. And then this famous conjecture proved by Denis says that this characteristic polynomial PIT, which is just the determinant of this Frobenius action, has an integer coefficient independent of L. L is always not equal to P. And the eigenvalues of the pullback action of Frobenius on eta common group are all algebraic integers having absolute value q to the I over 2. So actually there are three parts: the integrated part, the weight part, and also an independence part. But here we only talk about the two, the integer coefficients and the absolute value. So here is a remark. So this in this statement, this is statement equivalent to the following. So the eigenvalues, because this is for Frobenius action on this backspace, this QL backspace, so has a priori QL coefficient. So all eigenvalues are in this QL bar. So the statement equivalent to this the following: the eigenvalues in QL bar have been property that for any isomorphism, field isomorphism QL bar with C, this absolute value of iota alpha in C. So this absolute value is less than or equal to q to the I over 2. So here we need to choose. We need to fix field isomorphism iota. So this is also used in Anna's talk. So this is common in weight theory. So if we want to talk about the absolute value of a QR number, then we need to choose the isomorphism with C. Then embed this alpha into C. Then talk about the absolute value. Okay. So now we have the following motivation from complex from the kind of a complex dynamics for surfaces. So if F is the automorphism of a smooth complex project surface, we have this Lorentz group, which is just the group of divisors modular either algebraic equivalence or numerical equivalence, doesn't matter. And then we have the lateral including from this Lorentz group into the second column group. And then we consider lateral projection of this automorphism F on these two backspaces. So we have the following identities. The spiral radiance of, so these three spiral radii are the same. So the probe action on the Lorentz group, the action on H1 or the action on H2. So these three spiral radii are the same. So here the spiral radiance of a linear map is just the maximum of all absolute value of eigenvalues. So and moreover, the probe action on the transcendental part of this second column group has a finite order. Okay, because this one, this motivation is important later, so I will explain why these two these numbers spiral radius are the same. So the reason is quite simple. It's because this spiral radiance of this this automorphism F acting on Lorentz group is equal to this limit, the limit of mth root of this intersection number. So you take an ample divisor and then consider the probe action of this mth iterate Fm, and then intersect with this ample divisor again, you get a positive number. So the spiral radius is just the limit. And on the other hand, the spiral radius of this this spiral radius of this automorphism acting on H2 is also equal to the limit along the limit of this probe action of a Kähler form omega s. Okay, and because of the openings of ample cone or Kähler cone in this Lorentz group or in this second column group, then this equivalent definition of spiral radius is independent of the choices of this HI ample divisor or Kähler form. So then we just need to choose this Kähler form, or let this Kähler form be the first chain class of this OS HS, the ample line bond of this ample divisor. And then these two numbers are same. And the middle one, the spiral radius of F on H1 because it's lines between the two. So these all three must be same. Okay, so because of this factor from the complex surfaces, then Esnault and Srinivas proved a similar result in 2013 over finite field. So now X0 is the smooth project surface of a finite field FQ, and again S is the best change to a closure FQ bar. Then we take a automorphism of this surface. Then they prove that the spiral radius of this action on this total atomic ring is the same as the spiral radius of this probe action on divisors. And in particular, we have the spiral radius on this probe action on H2 is the same as the probe action on divisors. Okay, this is their result, and this identity is the same as this is what I said for surface for complex surface case. Okay, so the idea of their proof, so they use the classification of the surfaces in arbitrary characteristic. They also need to use a certain lifting argument for K3 surfaces, and for Abelian surfaces. They also need to use Tata's conjecture or Tata's theorem for divisors. Okay, So now here is the motivating question. Then we know this variance of the progression on divisors on second conic group are the same. Then what about the arbitrary self-morphism, arbitrary rational self-map, or more generally self-correspondence of smooth variety of arbitrary field? So, or rather, can we compare these two linear actions? So the first one is the progression of f on 2x eta conic group, and the other one is the progression of f on nkx. So nkx is by definition is here the group of algebraic cycles of quadrant k on x modular numerical equivalence. So this is a finite general Abelian group. If you tensor with a field, then you get a finite dimensional vector space. And we have seen this diagram from GSB's talk. So if you modular homological equivalence, we have embedding into a cohomology group. And we also have a suggestion map this AK to NK. And the standard conjecture says that we should have this injection, but without standard conjecture, this it's not clear. Okay, so now I need to talk about this dynamic degree in complex dynamics. So previously we only I only talked about this spare radiance, but it turns out in complex dynamics, this spare radiance is quite close to some dynamics property. So it's a special case of this dynamic degree. So in general, for a dominant meromorphic self-map of a complex manifold, then the case dynamic degree of this meromorphic map F is defined by the following limit. So the first limit, so as in the surface case, complex surface case, which we take the propagation of this mth iterate of this dominant meromorphic map on the case wedge product of this omega x, and then we take the cup product with omega x to the n minus k. Then we also get a positive number, and then take the mth root. So this is the definition of case dynamic degree, and this is equivalent to the other limits. The first one is we choose a norm on the cohomology group, the HKK, and then we consider the induced norm on this linear operator. Then this is also equal to the dynamic degree. And moreover, we can also consider the propagation of FM on the full 2K cohomology group, not just the HKK. And it turns out that all three are the same, and we give them the dynamic degree. And here the existence of a limit and the equivalence are due to D and Sibley by their work. Okay, this is the complex dynamics. We have these two invariant. This is dynamic degree, and this dynamic degree, why is one is related to the complex dynamics? Because the following theorem due to Gromov and Umedin. So their result says that if F is a holomorphic self-map, then the topological entropy. This is invariant in topological dynamic system. This entropy is the same as the so-called algebraic entropy, which is defined as the maximum of all logarithm of dkf, the dynamic degree of f. Okay. And moreover, in 2005, Dean and Sibley also proved consider the case when F is a dominant meromorphic self-map. So that proves that the topological entropy is always bounded above by its algebraic entropy. But this is for a dominant meromorphic map. Okay, so this is for complex dynamics for the meromorphic map of complex Cantor manifold. So So we are interested in algebraic setting. So if F is a smooth complex variety, and F is the dominant rational self-map, and now we choose the ample divisor HX, and then the case dynamic degree is also equal to the following limits. So first we replace the Keller form by this ample divisor as before. So we have the first limit, just replace the Keller form by ample divisor, and then use this first limit. We can also show that this limit is equal to the other two limits using norms, just as before. So the first is the norm of using the norm on this real backspace of address cycles, and the other one is as before, just the pullback action on 2K common group. Okay, so here again, so we need to use the openness of variance positive cone. So here, this property is important to deduce these equalities. Okay, so now we are almost arrived to this so-called dynamic degree comparison. So we are interested in this inequality, the limit of this pullback action of the pullback of mth iterator on the numerical group, and the pullback action on Tuyen's covenant group. So here we see that when X is a smooth complex project variety, and then we have this identity. But our question is, what about the arbitrary field? So when X is arbitrary, when X is defined over arbitrary field, NK is the group of numerical address cycles, and we give them norm. Here we also fix a field isomorphism QL bar with C as before. And then we also choose a norm on this QL backspaces using this field isomorphism iota. Then we have the following two definitions of dynamic degree over arbitrary field. So first, the so-called numerical dynamic degree, the lambda kf, which is defined as the limit of mth root of this pullback of this iterator using initiation theory, using the initiation of these ample divisors. And this first limit is equivalent to the second one using norms. So because we have the positivity of these cones, ample cones, and the other one is this so-called IS cohomological dynamic degree, so chi-IF iota. So this is the limit soup of this mth root of pullback on HI, the IS eta common group. Okay, so we have these two definitions. The first one, the lambda kf, the existence of limits and the equivalence are due to Tuyen. Okay, so our question is, are them the same? So this is a question asked by Tuyen in 2016. So for any k, the case numerical dynamic degree coincides with the 2K's cohomological dynamic degree, chi 2K F iota. So as I said before, this equality, this is true for complex project variety. So this is because we can replace these ample divisors by Keller forms, and then we go to common group. So they are the same. So this is not hard to prove. Oh, by the way, so in this definition, I use a dynamical correspondence here. So this dynamical correspondence is a generalization of a dominant rational map. So I will explain this one shortly. But right now, you can just think of this F as a dominant rational map, and this F diamond M is just the Euro composition of dominant rational maps. And for dynamical correspondence, we have the dynamical composition of for this dynamical correspondence. Okay, so now the interesting thing is that this conjecture, the dynamic degree comparison, this one can imply with the Riemann hypothesis. This is the reason is not hard to see, because if we take the Frobenius endomorphism, then because F is a morphism, then the chi the i's cohomological dynamic degree is nothing but the spare radiance. So because this one is just spare radiance, then with the Riemann hypothesis, this one is equivalent to the following. So all eigenvalues of this Frobenius action on i's automorphism group have absolute values at the most q to the I02 for any field isomorphism. So in other words, the i's cohomological dynamic degree of this Frobenius endomorphism with respect to this field isomorphism iota is less than or equal to q to the I02 for any iota. Okay, so this is a statement. We just translated the with Riemann hypothesis in a dynamical statement. So okay, so now using a standard product trick by Coulom's formula. So we just need to show that the two-case cohomological dynamic degree is less than or equal to q to the k for any iota. Okay, so now if we assume this DDC holds for Frobenius endomorphism, in other words, the chi2k is equal to lambda k, then lambda k of f is q to the k. So this lambda k of Frobenius endomorphism f is equal to q to the k. This is easy to show, easy to see, because f is because this f is actually a polarized endomorphism. So the pullback of this f on ample divisor is q to the q times this ample divisor. Then by definition of this lambda k, it's just q to the k. So yeah, you see that by definition of lambda k, it's considered pullback action on ample divisors. If f is the Frobenius endomorphism or polarized endomorphism, you always get qk here, q to the mk here. Okay, so here is another conjectural evidence towards this DDC. So if we assume standard conjectures, in particular, the standard conjecture of left type B and the standard conjecture of Hodge type. So assuming these two, and then by this Sayre's argument, so Sayre consider this Kählerin version of Weil's conjecture, but his argument works works only for Kähler manifold. So if you assume these two standard conjectures, then Sayre's argument also works in positive characteristic for all polarized endomorphism. So here polarized endomorphism means the pullback of this of ample divisor under this f is equivalent to q times hx. So conjecturally, the chi if is equal to q to the I02, independent of iota. But on the other hand, as I said, it's easy to see that lambda kf for this polarized endomorphism is q to the k. Okay, so if you assume standard conjectures, then we see that lambda kf is q to the k, and lambda 2kf is also q to the k. So standard conjectures implies DDC for polarized endomorphism. In fact, here we need to use standard conjecture of Hodge type for product variety for x times x. So for surfaces, this argument hasn't been completely worked out, because for surfaces you need to consider fourfold, as Joseph mentioned. Just talk the case of Abelian fourfold case is quite new. So if we try to use standard conjecture, the whole standard conjectures to solve this with Riemann hypothesis, it's quite hard. Okay, but we now know that we don't need to use the full standard conjectures. For example, the with Riemann hypothesis, this is the case of Abelian variety in any dimension for Abelian variety. This is proved by Weil himself at the very beginning. At that time, he didn't know any standard conjectures, and now we know that the standard conjecture of standard conjecture D was proved in 90s, and the standard conjecture of Abelian fourfold is also very new. So this makes us suspect that we may try to use another way to consider the Weil Riemann hypothesis without using standard conjectures. Okay, so this is a question. We just formulate this question called the eigenvalues of polarized morphism. So it's a positive characteristic of CS result. So CL proved this one for compact Cantor manifold, but we can formulate this one in arbitrary field. But if we consider in positive characteristic field, then this question is quite hard. So the case of Abelian variety, this is only known due to Weil. The case of Venetian morphism, this is nothing but a Weil Riemann hypothesis, and it's proved by Dunning. But other than these two cases, Katz told me that he doesn't know anything. So this question is also very hard. And in the end of the talk, I will talk about a new case about this conjecture in common surfaces case using our method. Okay, so now I will recall what the dynamical correspondence are. So first, the correspondence is just for correspondence from a variety x to y, it's just a algebraic cycle of codimension n. Here dimension n is the same as the dimension of x or y. All of them are equal, have the same dimension. But for in practice, we always need to consider some equivalent class. So we also need to use this definition. So this definition of correspondence sometimes may also be certain equivalent class of this algebraic cycle. So namely, this F is a correspondence is in Zn x times y with Q coefficients modulo certain adequate equivalence relation. And we also always need to fix a Weil economic theorem. So H x, so with coefficient correct 0. We have this couple product, and we also have a Poincare duality cross formula, projection formula, and also a cycle class map from algebraic cycles of codimension K into to this two-case common group. We also have a weaker left theorem. Sometimes when we try to talk about the standard conjectures of left type B, so we also need to assume the hard left theorem. But now we know that hard left theorem holds for an entire common group, but this is a corollary in Dunning's proof of Weil Riemann hypothesis. So in ours here, we should be a little bit careful about there might be some potential circular reasoning. Okay, so dynamical degree. So dynamical degree is just so first a correspondence is dominant. Means that any irreducible component of this Fi, we have the two lateral projections down to x and y. Then this correspondence is dominant means that these two projections are both surjective. And then dynamical correspondence is just effective and dominant correspondence. So it is first effective, and then the two projections down to x and y are both surjective. So for example, graphs of surjective morphism from X to Y, or graphs of dominant rational maps from X to Y are examples of dynamical correspondences, and also their sums. Okay, so we have we always have natural pullback and push forward actions of correspondence on numerical group and on cohomology group. This is quite standard in the second series. And we can also compose dynamical correspondences, just like how we compose dominant rational maps. So here we denote them by G, this diamond F. So G diamond means dynamical correspondence composition. Okay, then we let Fm, the diamond M, to let this one denote M's dynamical iterate of dynamical correspondence. But here there is a problem here. So in general, like composition of dominant rational maps, we don't have the following equation. So the pullback action on cohomology group or numerical group, they are not functorial. So we don't have this commutativity property. So if you pull back first and then take the M's iterate, this is not necessarily the same as the pullback for the M's dynamic iterate. So for example, you can consider the standard this standard Riemann evolution on P2. So if you consider the twice iterator is identity, so left side is trivial, but right side is not trivial. So this non-functorial nature of dynamical composition makes the computation of the dynamic degree very hard in general. So for instance, there is a conjecture in algebraic dynamics. So about the algebraicity of dynamic degree. So this one is just disproved very recently by Weil, Diller, and Johnson. So they gave an example. The dynamic degree is not an algebraic number. However, nonetheless, if F is a morphism, sometimes we consider the morphism case, for example, the Frobenius and morphism, or rather the graph of a morphism. Then we have this equation. So the pullback and the iterate, they are compatible. So in this case, the dynamic degree degrees are nothing but the spectral radii of certain linear operators by the spectral radii formula. So in this case, the situation is much better. Okay, so last year, Backdown and Charles Faber, so they gave a functional analysis characterization of dynamic degrees. So they interpreted these dynamic degrees of dominant rational self-maps as the spectral radii of bounded operators of uncertain infinite dimensional Banach spaces. So in our cases, all vector spaces are finite dimensional, and these pullback action are just a linear action on these finite dimensional vector spaces. So they construct some infinite dimensional Banach spaces, and then they interpret the dynamic degree as a spectral radii of these operators. So using this construction, they prove some new result. For example, about the degree growth of degree sequences. So, and also something about the algebraicity of dynamic degree. So dynamic degree in general may not be algebraic, but still we can consider certain cases. So they prove for affine three-dimensional affine spaces, then the certain dominant rational map do have the algebraic dynamic degree. So I think on Friday, Beck will talk about this result. So we could see his result on Friday. Okay, so now we have the dynamic degree comparison, but we can still have the following two other comparisons. So the first one is so-called spectral radii comparison, because we have two linear maps on finite dimensional vector spaces. We can consider if the two spectral radii are the same. or we can also consider if moreover these two actions, two linear maps have equivalent lengths. Okay, because of this diagram, which we have seen several times, we have the following easy inequalities. So first, the spiral radiance of F acting on numerical group. So this one is the same as the spiral radiance on AK, the algebraic cycle modular homological equations. And this is less than equal to the spiral radiance of the pullback action on the Tokai's common group. And also for this long. Okay, so we are interested in the other action. Can we bound this the action of this pullback action on common group by the action on numerical group? So now we have the following remarks. So because so here F, this F is circle M. This is the Euro composition of correspondences in the central sphere. So this correspondence is compatible with the pullback action. So if we use this composition instead of a dynamical composition, then affirmative answer to normal comparison could imply the spiral radiance comparison by this spiral radiance formula. And also, if we have the normal comparison, then we also have the dynamic degree comparison. So we just apply normal comparison to the mth dynamical iterator of this F. Then we have the dynamic degree comparison. So normal comparison is the most stronger one, the strongest one. The third one is that if we have a morphism F or a graph of morphism as a correspondence, then because this F is morphism, then we also have this so the pullback action of F is compatible with the iterate. So this two-case cohomological dynamic degree is also the same as the spiral radiance of this pullback action on H2K, and the same for lambda K. So in this case, when F is a morphism, then the dynamic degree are the same as the spiral radiance comparison. However, here is a negative news for this spiral radiance comparison or normal comparison. So this is why I call them questions, because if we consider a basis alpha I of the numerical group of coordination 1 divisors, and we also choose a dual basis of 1 cycles beta I, then we can consider the following correspondence. And this correspondence F is defined as delta X, the diagonal class, minus the sum of alpha I tensor with beta I. So if you consider this correspondence, then by the construction, the correspondence acting on algebraical on divisors is trivial, but it's non-trivial on the transcendental part. Here, transcendental part means the orthogonal complement of this algebraical 1 cycles. So it follows that the spiral radius on H2, the spiral radius of progression on H2 is non-trivial, so it's positive. But on the other hand, the spiral radius of progression on divisors N1 is 0. Okay, so therefore we are only focused on certain special correspondences, for example, dynamical correspondences, finite correspondences, or effective correspondences. Sometimes also correspondence of this special type, the AK cancel with the N minus K. So it's a natural question. So it's interesting to know to what extent this SRC or NC might hold. So right now we don't have a clear answer to this one, but we conjecture that at least this SRC and NC, they hold for effective correspondences. So here, this F by construction, this F is not effective. Okay, so now I will talk about our main result. So first of all, we choose intercompany group as our way common serial. The first result due to Truong himself, he proved in 2016 that if F is a surjective self-morphism of a smooth spectral variety of dimension n, then we have the following equation. So he proved that the spiralities of the projection of this F on the total cohomology ring is the same as the spiralities of this projection on the all address cycles. So here, n this n dot x means the direct sum of nk x for all k. So in other words, we have this maximum of all cohomological dynamic degree chi if with respect to any field isomorphism iota is the same as the maximum of all lambda k, the numerical dynamic degree. Because here we assume F is a morphism. So when F is a morphism, then the spirality is the same as the dynamic degree. Okay, so he proved the maximum of the two dynamic degrees are the same. So we know that. So if you remember the DDC conjectures says that individually lambda k is the same as chi 2k for any k. So he proved that instead of individuating the equality, so the maximum are the same. So, but as a consequence, the spiralities of the projection on total cohomology ring is the same as the spiralities of the projection on the cohomology group of even degree. So on this H2 dot x. Okay. So this equality, this has been also reproved by Kalacher, Vastenberg using dynamical data functions some 4 years ago. Okay, so the idea of the proof is as follows. So first of all, by Kaz and Messi, we know that as a corollary of Weil-Riemann hypothesis, the standard conjecture C holds over finite field. So in other words, the Coulomb projectors pi I are all algebraic. So using this one, then the left-trace trace formula can assert that the traces of this projection on Hi is the same as this initial number up to some sign. So first one is the graph of Fm, the gamma Fm is the graph of emissivity iterator of F times the pi 2n minus I, the Coulomb projection. And because standard conjecture C holds, this pi 2n minus I is algebraic. So right hand side is just a purely insane number of recycles. Right hand side is the cohomological. Left side comes from cohomology group.
What are the Tuyen projectors? What are the corresponding cycles?
We don't
so they come from intersecting with some correspondence.
Yes.
How do these correspondences look like?
So you need to use kind of so because this follows from the Weil-Riemann hypothesis. So
do you get explicit formulas for this?
Not explicit, but you can construct using, you can express this one as the polynomials of forbidden. But the polynomial is not explicit. Yeah. We can only say
so you apply this polynomial to some cycle and then you get this.
The polynomial of a graph of forbidden.
So it's a polynomial in the graph of the forbidden.
Yeah, like for, yes. So like, for example, if the graph of forbidden is given by f, then this pi I just some polynomial in terms of f.
How do you construct this?
You need to use some argument because these eigenvalues are co-prime. Then you can find some co-prime polynomials, such as their combination is the one. Then you can use that factor to get this Coulomb projector. Because Coulomb projector, the sum of all pi I is the one. In the diagonal class.
Is this written in a Katz-Messing paper?
Yeah. In Katz-Messing paper, yeah.
It's actually just a simple linear algebra.
Yeah.
If you assume if you know the Weil string, and it's linear algebra.
Okay, so then using this trace formula, so the traces of this pullback action is equal to some initial number. And the idea is we will try to give estimate of this initial number from of the right hand side. So the absolute value of this initial number is bounded above by some constant C, a uniform constant C, times the degree of gamma Fm and the degree of V for any effective cycle V on x times x. Okay, so you're using this estimate, then the degree of so here the degree of gamma Fm by definition is just the insertion number of the gamma Fm times ample divisors, the nth product of this this fixed ample divisor. So this is the standard ample divisor on this product variety. Comes from ample divisor hx on x using projection. If we expand this nth product, then we have the following sum by the standard combinatorial formula. And then inside this sum, each sum and ignore these coefficients, we have the pullback of this f m on hxi times hx n minus I, and this is nothing but this is due to give the definition of numerical dynamical degree. The numerical dynamical degree is nothing but the limit of the mth root of this initial number. Okay, so now if we take the mth root of the absolute value of this equation, the left side by linear algebra, so the left side is the square radius of the pullback action of f on this vector space, and the right side would be bounded above by the maximum of all numerical dynamical degree. Then we have this identity. Then we have this identity. So each chi if is bounded above or maximum of all lambda k, and then the maximum is also bounded above by the maximum of lambda k. But we know the other easy equality. Okay. So here we also discuss a non-uniform Hill-Shulsky non-way estimate on initiation number of a graph of forbiddance and correspondences tomorrow. So he will talk about this one. It's kind of a special estimate of initiation of correspondences, but for initiation with the forbiddance, and there is a uniform estimate. And here's my result in 2019. So I consider Abelian variety case. So for Abelian varieties, if f is a surjective self-morphism, then the dynamic degree comparison holds. So the square radians of the two linear actions are the same. So equivalently, the two-case cohomological dynamic degree is the same as the case numerical dynamic degree. So in particular, this answers a question of Esnault. She asked 10 years ago in this Riemann workshop. Okay, so the idea of this proof is as follows. So first of all, we know that the morphism Q algebra of Abelian varieties is very simple. Using this factor, I can show that all eigenvalues of this pullback on H1. So for Abelian varieties, because Abelian varieties, we only need to the most interesting in H1. So the pullback of F on H1 consists of n pairs. So pi1, pi1, pi2, pi n, and their complex conjugate. So we may assume that they are sorted in this order, and since the two-case eta common group for Abelian variety is nothing but the two-case wedge product of H1, then the chi2k of F, the two-case eta cohomological dynamic degree, is nothing but this product, the product of those pi I, because they have been sorted in the correct way. And then we call this product polynomial the product of t minus pi I arbiter polynomial of F denoted by PFA. So it satisfies this natural identity. The characteristic polynomial of F, which is defined as the characteristic polynomial of the pullback on H1, is the product of this arbiter polynomial and its conjugate. So in this sense, this arbiter polynomial is a positive analog of the characteristic polynomial of the analytical representation of this F for complex Abelian variety. And so let me recall that the lambda k, the case numerical dynamic degree, is defined as the limit of mth root of this unitary number. So now we denote by this f dac the Rosati evolution of F with respect to some fixed ample divisor Hx, and then we use this ample divisor to give a polarization of this Abelian variety to its dual x hat. Then the arbiter polynomial of this composition of this Rosati evolution and F, this arbiter polynomial is unique, satisfying the following property. So if we rewrite this arbiter polynomial of this composition as in this standard form, the sum of the alternating sum with some coefficient ck, then each coefficient can be written in terms of the product of those ample divisors.
You cannot divide by divisor.
Oh, no, it's not divided by divisor. So it's hx to the n.
Yes, the number.
Hx to the n. And it's a fixed number. So if you fix ample divisor, you get a fixed number. So
it's a rational number.
Yes, yes. Interesting thing is this denominator we have numerator we have this this number. So this number is close to the definition of a numerical dynamic degree. So we just need to replace f by fm, the mth iterator. Okay, so replace m by f to the m. Then the left side is the coefficients of arbiter polynomial of the iterate of those Rosati evolution and f to the m. So the right hand side is the right side is just the can be written as this elementary symmetrical polynomial in terms of those singular values of fm. Okay, so this sigma I are singular values of those f, because f is an automorphism. So if we embed those f into the automorphism ring, and then you will tensor with tensor with C, you get some complex matrices. And then the singular value just the corresponding singular value of those matrices. Okay, so now just by a basic calculation of those identities. So lambda k is the limit of the limit of mth root of lambda psi, but n choose k, n hx to the n, they are just constant. So after mth root, they will be gone. So lambda k just the limit of right side. So the limit of right side, because they are symmetric polynomial, so it's just equal to the maximum of all those I1, ik, such that all possible choices of this j from 1 to k. Okay, and then so for each one, the limit of this sigma I j fm 2 over m, this limit of this one will be just the eigenvalue of f. This is another linear algebra factor. The limit of this mth root of a singular value of the iterate of f will go to the eigenvalue. So this is a relation between singular value and eigenvalue. And then now we know we see that the maximum must be the first k indices. So it's equal to chi to k. Okay, so now I will talk about the other result on this quantitative version of this standard conjecture C. So before that, so we need to introduce this notation, the gamma R. This is the homological correspondence. So first, for any fixed rational number, positive rational number R, so we know by the Course formula and upon duality, there always exists a homological correspondence gamma R of X. So gamma R is in H2n, is a homological correspondence, and such that the pullback of the gamma R on HI is just the multiplication by R to the I map for each I. So if standard conjecture C holds, then gamma R can be just represented by correspondence, the sum of R I delta I. The delta I is the Course component. Okay, then the quantitative version of standard conjecture C we call conjecture GR. So it says that for any positive rational number R, the above homological equivalence is algebraic, and also it can be represented by a rational algebraic cycle GR, such that there exists a constant C, a uniform constant C independent of R, such that for any effective correspondence F, we have the following identity. The following inequality on this. So this the norm of this correspondence composite correspondence GR composed with F is bounded above by some constant C times the degree of this composite correspondence. So here the norm of GR, composed of the norm of correspondence is just the norm of this as an element in NN. And the degree, as I said, just the extension of the correspondence times the nth product of the ample divisor on product variety. So we also denote the degree kg. So use this one to denote the each summand of this from this sum. So it's the same as the product of the two cycles. Okay, I'll go quick. So the main results here about the conjecture GR is that so conjecture GR can imply inequalities of this type. So assume the conjecture GR if F is effective correspondence, so that the degree sequence is a log concave. For example, F is reducible correspondence. Then for any K, the square radius of the propagation on H2K is bounded above by the constant C times the K's degree. This is for even indices. For all the indices, the square radius of f on S2k plus 1 is also bounded by by the square root of this product is 2 degrees, 2 degrees. Okay, so the important corollary of this theorem is that, so if f is moreover effective and finite correspondence, for instance, graph of morphisms, then we have this dynamic degree comparison. So if we assume so this means that the conjecture GR can imply a dynamic degree comparison. And moreover, we also have the other estimate for cohomology dynamic degree of all the indices, the chi 2k plus 1. It also bounded by square root of lambda k times lambda k plus 1. And in particular, the positive characteristic analog of Sear's result, this also holds. So if we assume conjecture GR, so
can you one minute?
So as I said, so we can show that conjecture GR holds on Abelian varieties, and so we suspect that this is true for this conjecture GR is true for in general. And so conjecture GR could be an alternative way to approach generalized with limit hypothesis. And this is our application to Kumho surface. So besides Abelian varieties, we can deal with Kumho surfaces. So let A to X, so let S be the surface such that we have a dominant rational map from Abelian surface. For example, S could be a Kumho surface. So for this surface, we can show that first there is a uniform constant such that we have this inequalities of this type for dynamical correspondence. The left side is the traces of the pullback on common group. And secondly, we can show that using the first one, we can show that the dynamic degree comparison holds for dynamic correspondences that are algebraic stable. And the last one,
Sear's result is for singular cohomology of K.
Surface of K, and here K is always a direct closed field of arbitrary characteristic. So here this little K is a algebraic closed field of arbitrary characteristics.
Yes, Sear's result is a singular cohomology.
Yes.
Yeah, but when you speak about standard conjectures, it is for tau, the radical tau cohomology. Is it any Weil cohomology? Any.
Why cohomology?
Yes, but I mean here, how do you? Here you introduce this norm. You do this with any Weil cohomology?
Oh no. For the norm, we need to use eta common group.
Provided you have Weil complete theory that you can define.
Yeah. Right. For norms, we need to use eta common group. So you QL coefficient, and we embed in QL to C.
Yeah. In general, you can also have if you assume your complete is always define C with the space, then you can define norm.
Yes.
So you don't need LE complete, but you need some kind of like embedding maybe your field into C.
Yeah. So when your coefficient field of your common series can be embedded into C. So we chose the coefficient field F of the characteristic 0. So when you QL, if you can embed into C, then we can talk about log, then everything is okay. Yeah.
Let's define.
Yeah. So the last one is, so it's the positive characteristic of cell result holds for this kind of surfaces. I think I just.
Okay. Yeah. Thank you, Peter, for an interesting talk. Any questions?
Yeah. If you scroll back one. Yes. Here. When you say that conjecture GR is weaker than standard conjectures, which standard conjectures?
Oh, here. So conjecture GR. So we can show that for polarized homomorphism, standard conjectures imply this conjecture GR. The standard conjecture, the full standard conjecture, positive type and the electric type, and can imply conjecture GR for polarized homomorphism. But this conjecture GR is stated for arbitrary finite correspondences. So we suspect that this might be true for arbitrary effective correspondences.
Yeah, for example, you can prove this the conjecture GR for like two correspondences, then you can also prove it for like the sum of them. So kind of convex combination. Yeah, so it's possible you can prove this for. You can prove it for polarized endomorphism, then you can prove it for the sum of graphs of polarized endomorphism. So you get something more. Okay, so any other questions? If not, we thank Fei again, and then we have lunch pause, and then we start again at 3.